Hi, everybody. Welcome and thank you for joining our webinar, Everything You Wanted to Know About Floating Point Numbers and Didn't Know Who to Ask. I'm Misha Saint-Amand, Head of Marketing for JuliaHub, and today it's my pleasure to be joined by our presenter, Avik Sengupta, our VP of Engineering. Avik is the author of Julia High Performance, co-founder of 2 AI startups in the financial services sector, and creator of large, complex trading systems for the world's leading investment banks. It's really my pleasure to be here with him today. If you have any questions as he goes through his presentation, please put it in the Q&A and we'll answer them as we go along. Of course, just as many people ask as their first question, we will be sharing a recording of the webinar and any supporting materials with the registered attendees in the next few days. So now that I've gotten through that info, I will turn things over to Avik.
Thank you, Misha. Thanks for the introduction, and it's great to be here. Welcome, everybody, to this webinar. Hope you have a fun time for the next 45 minutes and hopefully learn something. As Misha said, if you have questions, type them in the Q&A window, and I'll get to them if I remember to look. If not, Misha will remind me, and I'll get to them as they come out. So we want it to be interactive, so don't wait till the end to ask questions. So today's topic is floating point numbers, which everybody works with, whether they are using Julia or any other programming language. You will, for any program that you write, you will usually end up using floats or decimals at some point. What we want to do today is do a little bit of a deep dive, things that maybe is not obvious when you are, given two floats and you're adding them or multiplying them, or even, adding or multiplying matrices of floats. We want to do a deep dive and see how they are stored on a machine, and what repercussions come about given how floating point numbers are represented on modern computers, right? There are various ways of doing this, through the history of computing. What we will talk about today is what is called the IEEE 754 floating points, which are today the standard way that floating point or decimal numbers are represented on almost all modern computers, right? So over the history, while many different representations have been tried, for the last maybe 30, 40 years, we have converged to a single way of doing floating point numbers, be it on Macs or Windows or Linux machines or ARMs or Intel chips, or even RISC-V chips, right? They all do the same thing. So with that preamble, what are we going to talk about today? First, as I said, we are going to talk about how these numbers are represented in memory on the CPU. We are going to look at a few special forms of numbers, right? Rather than, most numbers are similar, but there are a few numbers in the list of floating point numbers which are represented differently. So we'll look at that. We will look at something called fuse, multiply, add, or FMAs, which are ways of speeding up certain kinds of computation. We will look at big floats and double floats, and how to sort of go beyond the precision that regular floating points give you. And we will end with a brief discussion around SIMD. And that should hopefully take us at most for the next half an hour. and then we can, do questions and discussions at the end. So that's the schedule for today, right? So what are floating point numbers, right? What's floating is, I guess, the first question. Floating point numbers basically are used to represent fractional numbers, right? Numbers that are not whole numbers or integers. And the way that these numbers are typically represented in a computer is by storing the exponent and the significant separately, right? And one way to look at it is, the difference between writing them traditionally with a dot, with a point, versus writing them in scientific notation, right? So when you're writing them in scientific notation, the first part of the scientific notation is typically, one digit to the left of the dot, and then as many digits to the right of the dot as necessary, and then a 10 to the power x that represents the exponent, right? So, why, for the last one, if you write it in fixed point value, you will say 0.0000, so many 0667. But if you write it in scientific notation, you're saying 6.667 times 10 to the power minus 11, right? So the significant, which is, the bit which is not the exponent, is usually then between 1 and 10, right? Or between 0 and 10. And then everything else, how big or small the number is represented via the 10 to the power part of the number, right? So that's really what floating point means, in that you have a constrained range for the significant, and the size of the number is really in the power or the exponent that is used to write it out, right? So instead of writing so many decimal places, we will just write a number between 0 and 10 and then multiply it with an exponent. And so this, scientific notation is, of course, decimal, in that it is powers of 10, right? So we write the number, both the significant and the exponent is written as powers of 10. And so you can guess that when these numbers are stored in a computer, they are written as powers of 2, right? So, so the idea is similar. It's exactly like how you would write numbers as scientific notation, but with powers of 2 rather than powers of 10, right? So that's the key sort of feature that you need to know for everything that we see in the next section, right? So floating point numbers in a computer these days are typically stored as 64 bits of value, right? 64 binary digits. Alex points out a typo, and yes, of course, you would have seen when I said the number aloud, I think I said it correctly, but the number has a typo. Sorry about that. There's a minus missing. Anyway, so there are 64 bits of numbers, right? And that's float 64. Now, there is also float 32, which is half the number of digits, so 32 bits. But for the rest of this session, we will just talk about float 64. You can just half every value if you want to think about float 32. The reason why we talk so much about float 64 is that float 64 is an IEEE standard, and even 32-bit CPUs support 64-bit floating point numbers, right? So you may know that in Julia, the native integer type is different between 32-bit CPUs and 64-bit CPUs, right? But for floating point numbers, float 64 exists everywhere and is fast and native everywhere, right? So which is why, even in a 32-bit CPU, whether it be a ARM or Intel, 64-bit floating point numbers are standard and fast, right? So floating point numbers are stored as 64 digits. The first digit is used to store the sign, so whether it's positive or negative. The next 11 digits are stored the exponent, which is the power of 2. And then the final 52 store the significant, or sometimes it's called the mantissa, but the term mantissa is very overloaded. So, these days it's recommended that you call the fractional bit the significant, right? So that's how they are stored. So let's dig into this, what it means, right? So first, let's look at the sign bit. So there's a function in Julia called bitstring that takes any number and shows you the actual bits that the computer is storing in its memory, right? So a bit string of 1.0 is this long string 00, 1, 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0, and up to the end, right? Bit string minus 1.0, you will notice, is exactly the same, but the first digit instead of a 0 is a 1, right? So that shows that, if the first digit is 0, that's a positive number. If the first digit is 1, then the number is essentially multiplied by -1, right? And everything else is the same. So, other than the sign bit, the bit string of 1 and -1 are stored together, right? Now, to represent this, we have a function called float bits that I've written for this session, and we will use that going forward. And what float bit does is just separates out the sign bit, the exponent, and the significant, right? So you can see in this case for 1.0, the sign bit is 0, and then there's a bar that separates it out. The next part is the exponent, so that starts with a 0, and then it has 10 ones. That is the exponent, and the significant in this case is all zeros, right? So just the addition of these two bars make it easy to visualize the number, right? So we'll use this float bits number for the rest of the session rather than just bit string, okay? Excuse me. Any questions so far? Doesn't look like it. Let's carry on. So the second part is the exponent, which is the power of 2, right? So now this number 0 and 10 ones is a big number, right? It's actually 1023, right? Which you can see by converting this bit string into a int using Julia. So this number is 1023. And you'll think, why is it 2 to the power 1023? Well, actually, this number, the exponent is represented as the value minus 1023, right? So instead of just taking the raw value, the standard states that when you represent the exponent, you should take the value that is in these bits and subtract 1023 from it, right? So the significant, which in this case is all zeros, is basically interpreted as 1 point and then each of the bits, right? Now the point here is not a decimal point, it's a power of 2 point. So you can think of all the significance, so if the significant has 52 bits, so you represent the 52 bits or you value the 52 bits as 1 plus the bit 1 by 2 plus the bit 2 by 4 plus the bit 3 by 8, so on and so forth, up to the bit 52 by 2 to the power 52. So the place value of each of the digits of the significand is the power of 2, and then the bits are, 0 or 1, right? So putting it all together, this number, which we are saying is 1.0, is 1 plus, so all the bits are 0, which means the value of the significand is 1, right? So remember, just because all the bits are 0 doesn't mean the value of the significand is 0. Actually, the value of the significand is 1 because it is 1 plus the bits. So because all the bits are 0, the value of the significand is 1. The value of the exponent is 2 to the power 1023 minus 1023, so which is basically 1. So, and then you multiply the significand with the exponent. So, it's 1 times 2 to the power 0, which is 1. So the value of this number, which is 0 and then 0, 10 ones, and then 52 zeros, is actually the number 1, right? Does it make sense? That is essentially all you need to know about how these numbers are stored, right? So we can work through a few more examples. The next one is float bits of 1.5. So that starts with 0. The sign bit is 0, so that's positive. The exponent is again 1023. So the value of the exponent is 2 to the power 1023 minus 1023. And the significand in this case, you will notice, starts with a 1, right? So we have 1 plus the bit 1 divided by 2. So 1.5, which is 1.5, times 2 to the power 0, which is 0, and that's 1.5, right? If you do 1.75, you can do the same thing. It is 1 plus half plus 1/4, again, times 2 to the power 0, because the exponent hasn't changed. And that adds up to 1.75, right? Hopefully that all makes sense, right? So this is, it looks somewhat weird, but once you learn how to convert it, it should be pretty obvious what's happening and how it's stored, right? Make sense? In case you're wondering, why we are doing this subtraction of 1023, this is basically what's called 2's complement, right? So the exponent is stored in 2's complement style, while the significand is stored, as individual digits, which are just summed up, right? Okay, a couple more examples if you want to work through. In this case, we have float bits of 15. In this case, the exponent is 1026. So, you're multiplying 2 to the power 1026 minus 1023. So that's 2 to the power 3. And the significand is 111. So that's 1 plus half plus a 4 plus 8. That's 1.875 times 2 to the power 3, which is 8. So 1.875 times 8 is 15, right? Okay. Cool. Right. Now, so now this is a well-known fact, and the examples we have shown before should make it obvious that not all decimal numbers are representable as binary floating point number, right? So the number 1 by 10, which is the fraction 1 divided by 10, in decimal we represent it as 0.1, but in a computer, if you say 0.1 is greater than the rational number 1 by 10, in Julia you will see that is true, right? So 0.1 is actually not the same as 1 by 10. right? And this is sort of the source of all the confusion that people have about floating point numbers, right? So float bits of 0.1 is this number, right, that you can see on the screen. If you convert the actual floating point number 0.1 to a rational, you will see it's not really 1 by 10. It's this big number starting with 36 divided by another big number starting with 36. But you will see the last few digits are different, right? So it's almost a tenth, but not really. And if you do, the other way of looking at it is if you see the float bits of 0.1 and then many zeros 0.1, right? You will see that the representation of that floating point number is exactly the same as float bits of 0.1, right? So float bits of 0.1 is this number here. Float bits of 0.1000 so on 1 is this number here, right? Or this representation here. And this, this and this are exactly the same, right? So a computer cannot differentiate between 0.1 and this number here, right? Because their bit strings are exactly the same, right? So that's basically the problem with floating points, in that, two numbers which are close together, as far as the computer is concerned, they are exactly the same, right? Right. One way to sort of represent this is an idea called the machine epsilon, or EPS, right? And so in Julia, there's a function called EPS, which if you call EPS on 0.1, it gives you this 10 to the power minus 17 order number, right? Which is a small number. So EPS is basically the difference between 0.1 and the next representable floating point number on the computer, right? So we saw that 0.1 and 0.000000001 are not representable separately. But then what's the next number that is actually representable? And if you find that, the difference between 0.1 and that number is 1.36 into 10 to the power minus 17, right? And that's the definition of EPS. So we can do some working to figure out what this is. So let's say float bits of 0.1 is what we saw before. Let's take that representation of 0.1, right? This, and then, let's take the representation of 0.1, which is this, right? So this is basically, you will see the same as this number here, right? So this is essentially the same as float bits of 0.1. Now we take this number and then we change the last 0 to a 1, right? So we convert this, which is everything the same, except the least significant digit has been changed from 0 to 1, right? And then we compute the float 64 of this number, the float 64 of that number, and the difference between the two is EPS, right? So that's the definition of EPS. So this cell here basically shows you how the EPS function essentially computes, right? Another way of looking at this is there's a function called next float. So you can say next float of 0.1 is basically this number, 0.1, many zeros and 2. And you see, like, it is, greater than if there was 1 in this number, in this place. If there was 1 in this place, we saw that we couldn't separate it, we couldn't represent it separately from 0.1. But if there is 2 in this place, which is a greater number, then that is representable, and that is next float. And so, if we compute the float bits of this next float 0.1, you basically get, this difference is the last significant digit over here, right? So that's essentially next float. Next float is, change the least significant number, a least significant digit of a floating point number, and then what's the next number that you get. Okay. Any questions so far? Hopefully this all makes sense. Okay. So that was all about sort of the low level, representation of numbers and how they are stored, and so what repercussions it has. Let's look at some results of that, right? So a zero is basically, zeros as exponents and zeros as significants, right? So that's a zero. But you can also have a minus zero, right? Now, a zero and minus zero in mathematics is essentially the same, but in IEEE floating points, minus zero is represented differently from plus zero. And the difference in representation, as you would expect, is basically this number in the sign bit, right? So the sign bit for the positive zero is zero, the sign bit for the negative zero is zero, right? But in Julia, if you say 0.0 is equals minus 0.0, it will show you true. But if you use the triple equals, which is Julia's sort of deep equivalence relationship, it will show you as false, because the internal representations of plus 0 and minus 0 are different. But the mathematical value of plus 0 and minus 0 are the same. And so 2 equals gives you true, but 3 equals gives you false, right? And as you can see, the reason why triple equals gives you false is that in the bits, there is one bit which is different. And so you can, differentiate between plus 0 and minus 0, right? Infinity is represented with an exponent of all ones, right? So you saw, even for the highest exponent, 1023, it started with a 0, and then those were all ones, right? If all the exponent numbers are ones, then it's an infinity, right? And it doesn't matter what the significance are, so long as all the exponents are 1, it's an infinity. And again, like a 0, if you switch the sign bit, then with a sign bit of 1, it's a minus infinity, right? So again, even though, infinity can be represented on both sides, so you can have negative infinity and positive infinity, both are representable within floating point numbers. Okay. Not a number is represented as an exponent of all ones, like infinity, as it happens, but a significant of non-zeros. So for an infinity, the significant has to be zeros. If the significant is non-zero, then it's not a number, right? Now, the thing about not a number is that the significant can be anything, right? Any of the bits, if it is 1 or more than one of these bits are 1, it'll all be not a number, right? So which means that there are, lots of not a number representations in IEEE floats. It's not just one number which is not a number. There are, in fact, millions of numbers which can be represented as nans, right? So, something about nans to keep in mind is that no two nans are equal to each other. But, when you say equivalence or triple equals, then the nans are true in Julia. But generally, any nan is not equal to another nan, right? And that's true in Julia and most other languages, right? Okay, the final special form that we will talk about very quickly actually is something called subnormal numbers, right? So subnormal numbers are basically numbers in which the significant has leading zeros, right? In general, when we were writing, think about when we were writing um, scientific notation, right? When you're writing scientific notation, the base, the significant you write as 1 point something, right? Into 10 to the power minus 20 or whatever, right? You would never write 0.02 into 10 to the power minus 4. You would write 2 times 10 to the power minus 6, right? So you would never put a leading zero in a significant, which is also true in floating point numbers. Usually, you would never put a leading zero in the significant. If there is a leading zero in the significant, you would basically shift it and then, add to the exponent, right? So that's how you represent normal numbers. But if you start to put significant zeros in the significant, then that becomes a subnormal number, right? And the reason why subnormal numbers exist is to give you a gradual underflow, so that the minimum number representable becomes smaller and smaller in floating point. You don't just jump to 0 from a smaller number. You can go smaller and smaller and smaller, and that is useful in some situations, right? So numbers of the order of e to the power 10 to the power minus 308 is probably the first subnormal number that you can represent in floating point, right? Now, why are we talking about it? Because subnormal numbers, they are helpful for sort of erroneous division by zero error. So if your divisor is very small, sometimes you would have normally got a division by zero error. But if you have some normals, then you actually get a better underflow. So there is a function called is subnormal, which tells you whether any number is subnormal or not, right? So again, to sort of give you a sense of why do subnormals sort of is a concept in general, why are we worried about it? That is because in some situations, subnormal numbers can have performance impact, right? Particularly on Intel machines. I am told on AMD machines, the impact is much less, but I'm not 100% sure. But on my machine, which is an Intel machine, I'll show you an example. This function is a this function is a heat flow function, which basically does an exponential reduction, right? So there is the possibility of underflow. And so, the details of the code are not important. What we do is we run this function once by doing something called set subnormals, set zero subnormals. What that does is that whenever a number is subnormal, the number is taken to be 0, right? And that speeds things up because the CPU doesn't need to worry about subnormal. So what we do is we run this 6 times. For every odd trial, for every even trial, we set subnormals to 0, and every odd trials uses subnormals normally. And you can see that, the even trials are quite a bit faster, right? So 272 milliseconds versus 119 milliseconds. And so there's about a 2x performance benefit to using subnormals to 0, right? And so you can set this if you want, very high performance, but you have to be sure that your compute is stable enough that even with some normals as 0, you get the correct results. But this does allow you to get some additional performance on, some kinds of performance. Chloe has a good question, which is how are subnormal numbers represented if the significant bits are interpreted with a minimum of 1? Well, yes. So if there is significant zeros in the significant, that's a mouthful. If there are significant with a T zeros in the significant with a D, then the interpretation is actually 0 plus rather than 1 plus, right? So that switches the interpretation, and that's why some normals are sort of different, and they are handled differently by the CPU, and their interpretation is different, right? So you can't just do standard bit operations for the addition or whatever the CPU does, right? Hopefully that makes sense. Right. Moving on. Rounding, right? So we talked about the fact that not every number is represented in floating point values, right? So what happens is when you're adding two numbers or multiplying two numbers, or more importantly dividing two numbers, right? Mathematically, you might reach a number that is not possible to be represented in the floating point number, right? So then what the CPU does is basically round things to the nearest floating point number that is representable, right? So here, one way to show that is to actually use big floats to compute. So for example, if you add 0.1 to and 0.2, you would expect 0.3, but what the computer gives you is 0.3 and then many zeros and 4, right? And so this is basically the rounding error that you get due to the limited precision of floating point, right? So you can get more precision by using big floats. And so if you convert 0.1 to a big float and 0.2 to a big float, then you will see that instead of getting 4 in this position here, you get 0 to this position and then a 16653 at the lower significant positions, right? So this is the amount of significant digits that you have in a big float, right? A big float typically, I think, has 512 bits of precision, if I'm right. Someone can correct me if I'm wrong, but I believe by default, the big floats that we use in Julia have 512 bits of precision, while float 64 has obviously 64 bits of precision, right? So you can get more precision on using big floats, but without using big floats, on standard 64-bit, you will always get these rounding errors. And that's, if you're doing any numerical analysis, you have to worry about whether your computation is blowing up, right? One way where these rounding errors can affect you is, for example, associativity, right? So floating point operations, because of this rounding, is not associative. So for example, if I say 0.1 plus 0.2, add that first, and then add 0.6, 0.3, I get 0.600000001. But if I do it the other way around, I get 0.6 exact, right? Because of the rounding that addition implies, or because of the imprecision of addition, the addition operations are not associative, right? So one way it can blow up for you is if you're calculating the sum. So in this line here, I'm calculating the sum of 1, 10 to the power 100, or 10 times 10 to the power 100, another 1, and 10 minus 10 times 10 to the power 100, right? So now this and this should cancel out and I should get 2, right? But I don't. So this gives you 0, although the correct answer is 2. So that's a huge error, right? And this comes about because you're adding 1 and 10 to the power 100. So you have two numbers which are very different, and you add the two, and that causes the error. One way to fix it is do things sort of in a different order. So let's say I do it like that, right? Not like that either, actually. Plus 1.0 plus 1.0, right? And if I do it like that, that gives me a 2, right? But in the different order, it was giving me a 0, right? So when you're summing things, the order is important, right? So if you're summing an array, what do you do? Well, one way to do it is actually sort your array by size and then add it that way. That's a good way to sum, actually. So if you have an unordered array and your numbers are in a huge range, then you're better off sorting it. Or you use something that is called Kahan summation, which actually does it better. So the previous the previous sum that I had, using sum KBN from the Kahan summation package, gives you the right answer. However, Kahan summation is not perfect. It still has this some amount of floating point rounding. Just because two additions themselves can give you rounding, and so you will get some rounding. It is not perfect, but it does handle the case of very big and very small numbers, right? Okay. Speeding up a bit, actually. Another way that you get rounding is cancellation when you're subtracting two numbers that are very close together. So if you have a function called 1 minus cos x by x square, and you pass a very small number to it, you want actually 0, because your answer should be near 0, because cos of 1.2 into 10 to the power minus 8 is almost 1, and you're subtracting 1 from, almost 1 from 1, and the answer that you get is 0.77, which is very, very wrong, right? What can you do? One solution is you can rewrite it to an equivalent form without subtraction. So, 1 minus cos is half of sine x by 2. And if you write it like that, then you get the correct answer, even with small inputs, right? Okay. One way to also solve these problems is to use special functions. So if you have sine pi, you get 0. If you get sine of 1,000,000 pi, you still want a 0, but there is rounding error and you get, this number. But if there's a function called sine pi, and you pass 1,000,000 to it, and you get a 0. So Julia has all these special functions which are useful to get these values which are traditionally difficult to compute. So for example, there's a function called expm1, which computes exp minus 1, which is a very useful and a very common thing to calculate, right? E to the power x minus 1. And expm minus 1 calculates it accurately because, again, a subtraction of 1, if the first number is near 1, then you get sort of catastrophic rounding errors, right? Fuse multiply add is a special operation that can add and multiply. So, a times b plus c, you can do it in one operation. So FMA, you will see that this is one assembly operation that can, do one multiplication and one addition. And again, doing this is very common. A times b plus c is a common operation. And if you're doing it in a loop, then using an FMA is very useful. One place where FMA is useful is, for example, if you get, again, so you're subtracting something, you get catastrophic cancellation. If you say square root of b square minus 4ac, you're solving a quadratic equation. If b square and 4ac are similar, you can get a rounding error and you get a negative number, and the square root of the negative number, you will get an error. But if you compute it using FMA, you will get a more accurate result, and then a 0 will be a real 0, and you will get the correct result again, right? Which is and now FMA, depending on the CPU, can be faster or slower. So you should maybe use a function called mulad, which uses either FMA or native operations, and chooses the right answer, chooses the right value, the right methodology, and it's typically faster than just using FMA directly, right? Okay. Big nums are, we've talked about big nums before. We talked about big floats. Big integers are used mainly to prevent overflow. So, if you have an integer, the maximum integer is this number here. If you add 1 to it, famously, it'll, overflow and you will get a negative number. But of course, if you do big nums and add 1 to it, that will not overflow, right? You will get the next number. So that's sort of standard. But for our purposes, we want a big float. Now, for big floats, floating point numbers don't have the overflow problem, right? Because the maximum overflow maximum type float 64 that you can get is actually infinity. So what you get with big float is more precision, right? So if you want, you want more precision, more digits in your number, your rounding errors are less. That's what big floats give you. The downside of big floats is that it is really, really slow, right? It's like 100,000 times slower sometimes than using native floating point. So you really need to be sure that you need that precision before you use big floats, right? One sort of halfway house is something called double floats. So what double floats are is actually two floating point numbers put together, side by side. They are stored side by side in memory, and they give you additional precision, right? Generally, if you have float 64, you think, okay, the next thing is float 128. But float 128 is not native on the CPU, and Julia and LLVM doesn't have float 128. I think LLVM is getting it, but Julia doesn't wrap it properly. So you can't have float 128 very far, fast float 128 in Julia yet. So double floats is pretty good. It's slightly less precision than float 128, but it is much faster than big floats. It's slightly slower than float 64, but it is order of magnitude faster than big float. So if you want a little more precision, right, you convert your floats to double floats, do your operations, and convert it back, right? So in this case, I have an array of random numbers, and I can add it. I think that's the one. I have an array of random numbers. I convert them to double 64, which is the double float type, and then I add it, and I get a little bit of extra precision, compared to adding that large array directly, right? The final one, very quickly, it's probably a webinar by itself, is SIMD. So we will, I will just talk about it very quickly. SIMD is basically the idea that the CPU does many operations in parallel, right? Instead of, you're adding a million numbers in an array, instead of adding one number a million times, it will add 8 numbers together or 16 numbers together, right? And that's basically the idea. In Julia, you can use this SIMD macro to get SIMD operations. So for example, this loop that essentially just adds numbers in a vector, one by one, you can annotate it with @SIMD, and you will see that this uses these VAdd PDs, which are these one VAdd PD adds maybe 8 numbers together, but then it's also in line. So you have 3 VAdd PDs, one after the other, and that basically adds many more numbers in one loop, and that again speeds things up. You can check the output compared to a sum basic, which just adds numbers, and you will see here that it does use some SIMD operation, this VAdd-SD, but it's only one VAdd-SD. So even without @SIMD, Julia does some SIMD conversions automatically, or LLVM does it, but it's not optimized to the level that @SIMD can do, right? And so if you compare the two, you get my sum, which is with SIMD, is 144 microseconds on my machine, and without SIMD is 861 microseconds. So in this, it's maybe 7 times faster, 6 times faster, just using SIMD. So if you're doing floating point operations, and you're doing things in a loop, you're doing things on arrays, try adding SIMD, and you might just find things becoming faster, right? So I think I've sort of gone on for quite a bit longer than I expected, but we did answer a few questions while we were going on. If there are any other questions at the end, I would be more than happy to take them. If you want further readings, the IEEE standard is not very difficult to read. And in terms of books, I think the best book around floating point numbers and rounding, accuracy, numerical stability is a book by Nicholas Hyam, which is which you should read if you're interested in this topic, right? It's a really, really good book, right? Right. If
Well, I don't see any additional questions, but you are welcome to reach out to us one-on-one if you prefer to ask your question that way. You can respond to the email with the webinar recording, and we're happy to follow up to answer any questions you might have from this webinar. Avik, anything else to share?
No, I think this notebook, as Misha said, I'll put it up at a public location, and we'll send you the link. You can then play around with it, change stuff, and see how it goes. So hopefully you'll have some fun playing around with the code on this notebook.
Excellent. Avik, thank you very much. Thank you to all our attendees for joining us today. And we look forward to seeing you at our next webinar. Thank you.
Thanks. Thanks, folks. Have a good day. Bye-bye.